Over the last few lectures, we have been taking a look at the mathematical properties of the Lorenz transformations and their bigger cousin, the Poincare transformations. In today's lecture and the coming ones, what we are going to do is we are going to connect these mathematical features with quantum mechanics. In particular, we are going to talk about the possible behavior of one-particle states in quantum mechanics when you go from one inertial frame to another, that is, under a Poincare transformation. Now, as a result, we will get very valuable information about the behavior of single particle states. Not only that, this analysis will tell us what kind of single particle states are actually possible. So, I'm pretty sure everybody has heard about scalars, vectors. Some of you who have done advanced quantum mechanics courses would also know about spinors. What we are going to do is try to take a unified look at all of these, and rather than think of them as individual kind of objects, try to see how those objects are consequences of the basic mathematics which is there in the Poincare group. So before we go there, let us take a look at what we have already learned about the Poincare group. So this is a quick recap of what we have already done. So let me now do a quick recap of the properties of Poincare transformations that we have seen already in previous lectures. As you all must remember, a Poincare transformation is one in which space-time coordinates transform in the following manner. X goes over to x prime, which is given by lambda x plus a. Here lambda is a 4x4 matrix and A is a 4x1 vector. In components, this equation looks like x prime mu equals lambda mu nu x nu plus A mu. And the additional property that such transformations must obey is the following. Because of Einstein's second postulate, the invariance of speed of light for all observers, we end up with eta mu nu lambda mu rho lambda nu sigma must be equal to eta rho sigma. As an immediate consequence of this, we can show that the determinant of this matrix lambda must be either plus 1 or minus 1, and also lambda 0, 0, the purely temporal component of lambda, must be greater than or equal to 1. Now these Poincare transformations have the following composition rule, which is very easy to figure out algebraically, that if you carry out a transformation with parameters lambda and a first, and then carry out a transformation with parameters lambda bar and a bar, the resulting thing is a single transformation given by parameters lambda bar lambda for the Lorenz transformation part and lambda bar a plus a bar for the translation. And a direct consequence of this is that the inverse of a Poincare transformation with parameters lambda and a is another Poincare transformation with t of lambda inverse minus lambda inverse a. Now, as I already said, that for all Poincare transformations, or rather for the Lorenz transformation part of the Poincare transformation, you have det lambda equal to plus or minus 1, and lambda 0, 0 is either greater than or equal to 1, and I perhaps forgot to mention that. It could also be less than or equal to minus 1. Now, all of the Poincare transformations together form a group, but it has a very important subgroup, that of proper orthochronous transformations, which have determinant of lambda equal to plus 1 and lambda 0, 0 is greater than or equal to plus 1. Now, this particular subgroup of the Poincare group is connected continuously to the identity. So it has to be implemented in quantum mechanical terms by a unitary operator. So psi, the state, goes over to psi prime, given by u of lambda a psi. And we have assumed that you do not have projective representations for, at least you do not need projective representations for Poincare transformations. So you have u of lambda bar, u of lambda a is given by u of lambda bar lambda, comma lambda bar a plus a bar, which exactly mimics the way in which Poincare transformations combine. We then took a look at infinitesimal Lorenz transformations, where we saw that the for infinitesimal transformations, the translation A can become an infinitesimal vector epsilon, whereas the Lorenz transformation matrix lambda must be very, very close to the identity. So we can write that as identity plus omega. And this omega has a property that omega rho sigma equals minus omega sigma rho. Note that this works for omega with two lower indices. And for a new infinitesimal Lorenz transformation, or the Poincare transformation like this, we can write the corresponding unitary operator as one which deviates very, very slightly from the identity operator, which we have denoted by 1 here. The additional piece is I by 2 omega rho sigma, j rho sigma, minus I epsilon rho p rho. This introduces to us the generators j rho sigma and p rho for the Lorenz transformation, and we have these properties. J rho sigma is minus j sigma rho, and j rho sigma's adjoint is j rho sigma, so this is Hermitian, so is p rho. We then went on to talk about the way in which the Poincare group generators j mu and p mu transform under Poincare transformations, that is when you go from one inertial frame to another. Now, what we found out is that this particular similarity transformation, which talks about the way in which the operators transform from one inertial frame to another, is given by these relations. And what they say is that under a Lorenz transformation, j rho sigma form components of a contravariant second rank tensor or a rank 2, 0 tensor, whereas the components of p mu actually form a 4 vector, that is so-called contravariant vector in older notations. These terms actually tell us how angular momentum changes when you carry out a translation of coordinates. By the way, some of you may have noticed that these equations are not the ones we had derived in the previous classes. These are the ones which Weinberg writes down. We had talked about the inverse of this transformation, which directly talks about how vectors and covectors transform. And they look slightly different, but they have exactly the same content. We then went on to talk about what consequences these equations would yield if we were to replace the u lambda a by an infinitesimal transformation, and this will give us commutation relations between the various Poincare generators, which is called the so-called Poincare Lie algebra. And we found out the following commutation relations. And although the commutation relations look pretty crazy and complicated, especially the ones between j mu nu and j rho sigma, it turns out that they are really not that difficult, especially given the fact that etas are diagonal matrices, so most of the terms vanish anyway on the right hand side here. We also saw that we could actually relate these generators to things which we know or we are more familiar with from non-relativistic quantum mechanics, like J1, J2, J3. The three components of angular momentum can be identified with the generators J23, J31 and J12 in that order. P1, P2, P3, the three components of spatial momentum, familiar operators from quantum mechanics, are really the spatial part of the vector P mu, P upper 1, P upper 2, P upper 3. The new quantity which we don't talk about in non-relativistic quantum mechanics are the boost generators K1, K2, K3, which are J01, J02, J03. And the 10th generator that we have, P0, is nothing but our familiar Hamiltonian. We also saw, and for reference I'm writing this down, that we could write this identification of the angular momentum operators more compactly as Jij is given by epsilon ijk jk, and its so-called inverse relation, Gi is half epsilon ijk jjk. The Ki's are easily seen to be J0i's. So these identifications will come in handy for various manipulations that we are going to do in future lectures. Finally, that is finally as far as the recap is concerned, we saw that there are certain subgroups of the Poincare group for which the unitary operator which is acting on states can be written down explicitly even for finite transformations. These are the cases where the parameters add up. One of them is a case of pure translations. So under I, A, that is no Lorenz transformation, just translation, the unitary operator corresponding to that becomes e to the minus I A mu P mu, which is just a result of exponentiating the infinitesimal version, which of course can be expanded out in e to the I A0H minus I A vector dot P. Remember, according to Weinberg's notation, he is using eta 00 equals minus 1 and eta 11, eta 22, eta 33 equal to plus 1. So, he is essentially using the positives more metric. In addition to that one, another subgroup for which it is very easy to find out the finite version for U is that given by rotations about a particular axis n hat. And for such a Poincare transformation, which corresponds to a Lorenz transformation given by r n hat theta, rotation through an angle theta about the n hat axis, and no translation whatsoever, the corresponding unitary operator is a familiar one from non-relativistic quantum mechanics, which carries over to relativistic quantum mechanics as well. This is given by e to the I j dot n hat theta. This was a recap of whatever we have done in the past series of lectures. Let us now make use of this background to study how physical states in quantum mechanics transform under Poincare transformations, that is, transitions from one inertial frame to another. We will focus primarily on one particle states and talk about how they transform. We will see that this will also help us to classify all possible one particle states. Now, to begin with, note that we have this commutation relation among the components of the momentum operator. These are, of course, the momentum 4 vector, which includes the Hamiltonian as well. And we have seen that they commute among each other. The generators of translation, which are these P mu's, they commute among each other. So it would be natural to talk about physical states which are simultaneous eigenstates of all of these 4 operators. So the kind of states we will focus on are states which obey this. They will be labeled by small p, whose components small p0, p1, p2, p3 are going to be eigenvalues of these capital P mu operators. So we would like something like this. However, as is very often the case, just labeling or just specifying what the eigenvalues are for the 4 momentum operators, 4 components of the momentum operator, may not be sufficient to pinpoint the state completely. You may need additional labels. In other words, capital P mu's may do form a set of commuting observables, but they may not form a complete set of commuting observables. You may need further observables to be added to this list so that their eigenvalues will also label the states, and ultimately once all the labels are given, you can say for sure which state we are talking about, at least up to multiplication by a complex phase factor. So we need additional labels, so let's put them in. These sigmas, they signify the additional labels that you will need to ultimately specify the state completely. For a general quantum state, which may contain multiple particles, these sigma labels can be continuous as well as discrete. So there could be some of the labels which are continuous, some other labels which are discrete. However, if you're talking of single particle states, then we take as part of the definition of a single particle states that these sigma labels will only be discrete. In fact, that will be part of our definition of what a single particle state is. So whatever we said up till now actually is valid for all general states. Of course, all general states are not momentum eigenstates, but we can label a complete basis with eigenvectors of the momentum, simultaneous eigenvectors because they commute, in addition to eigenvectors of other observables from which you will get those labels sigma. And these sigma labels being discrete is what we imply when we talk of single particle states. Now, one result that we had talked about just a while ago is the following. The unitary operator which acts on quantum states specifically for translations can be written down explicitly for finite value of the translation, and we saw that this is what its form is. So we know immediately what happens to these states psi p sigma under translations. So this is a translation of coordinates from one observer to another, and under that the state psi p sigma, which is just to the minus I a mu p mu acting on psi p sigma, takes this very simple form. Because psi p sigma are eigenvectors of these operators p mu, you immediately get the minus I a small mu p upper mu. So these are just numbers now, psi p sigma. In other words, under translation of coordinates, these wave functions psi p sigma just pick up an extra phase factor which is given by e to the minus I a dot p, the scalar product of the translation vector and the 4 vector depicting the momentum of the particle. What we are trying to do here, note, is figure out exactly how these states are going to transform under Poincare transformations. Poincare transformations are actually compositions of Lorenz transformations and translations. What we have done right now is figure out exactly how translations are going to affect these states. So all that is left is figuring out how these states are going to be affected by a Lorenz transformation. And that is what we are going to discuss next. So the kind of transformation that we are looking at now are pure Lorenz transformations, that is no translation, just a Lorenz transformation lambda. And this of course corresponds to a unitary operator acting on my states given by u lambda 0. And we are going to abbreviate this with just u of lambda. So this unitary operator acting on psi p sigma produces a different state. And it should be rather easy to understand intuitively that if you carry out a Lorenz transformation, the new observer will see a different momentum, 4 momentum from the old observer. In fact, we already know what kind of different 4 momentum is supposed to see. That is nothing but the transformation matrix lambda acting on P. Remember, 4 momenta are 4 vectors, so they transform exactly the same way as coordinates do. So under the Lorenz transformation, x changes to x prime equal to lambda x. So we intuitively expect P to change to lambda P. And let us just check whether that really happens. So to check this, what we need to do is start with u lambda P, u lambda acting on psi p sigma, and then see exactly what p mu gives when it acts upon this state. So to understand this, all you need to do is move the u lambda from here to this side. That is, you put in a u lambda on the left of the whole expression. Of course, you can't really do that because p mu does not commute in general with u lambda. Note that p mu does not commute with the generators of Lorenz transformations. They only commute with other generators of translation. So, moving this u lambda right across p mu is really illegitimate, but what you can always do is this. Put in a u inverse lambda pair on the left of the whole expression and then complete the whole thing. And this is where our information about the way in which the generators transform under Poincare transformations come in handy. We had worked this out in the last lecture. I had also recapitulated this at the beginning of this lecture, but there, unfortunately, I had just copied down Weinberg's version of it, which talks about U lambda P mu U inverse lambda. What we need is this particular thing, which I had actually worked out explicitly. U inverse lambda P mu U lambda turned out to be lambda mu rho P rho. This is exactly what you mean when you say momentum transforms like a contravariant vector picks up these lambda mu rho factors. So using that, we can immediately write this down as U lambda times, this is of course lambda mu rho P rho acting on psi P sigma. And now you have the momentum operator P rho acting directly on momentum eigenstates. So this of course gives us lambda mu rho and the numbers P rho, the eigenvalues. And since these are just numbers, you can pull this out. Lambda mu rho P rho of course is nothing but the mu-eth component of the vector lambda P, and you have U lambda acting on psi P sigma. So note that the momentum operator P mu acting on U lambda psi P sigma gives you U lambda psi P sigma, the wave function back, multiplied by this number, lambda P's mu-eth component. So this clearly shows that U lambda psi P sigma is an eigenstate of the momentum operators again, but this time with eigenvalue given by the momentum lambda acting on P. Not P, but lambda P. So basically, we can, given the fact that we have already written down a notation for eigenstates of the P mu operator corresponding to eigenvalue small p mu, we have just written them as psi P sigma. What we have here are eigenstates of P mu again, but with eigenvalue lambda P. So you expect U lambda psi P sigma to be an eigenstate of the P mu corresponding to eigenvalue lambda P, and therefore this is the label which goes in. But now we have to be a bit careful because the other labels might also transform when you act upon psi P sigma with U lambda. In other words, you may end up not with psi lambda P sigma, but a superposition of psi lambda P sigma primes over all possible sigma primes with appropriate coefficients C sigma prime sigma. And C sigma prime sigma of course will depend on which P you start with and on which particular Lorenz transformation you are carrying out. So despite the rather complicated appearance here, this is just a numerical coefficient. All you are saying here is the following. You know that when U lambda acts on psi P sigma, you are going to get an eigenstate of capital P mu, simultaneous eigenstates of all the four components with eigenvalues given by components of small p mu, acted upon by lambda. The components of lambda p with eigenvalues given by the mu-eth component of the vector lambda p. So what we know now is that this result has to be a superposition of all possible states which have lambda p as eigenvalues for capital P mu. So they could be psi lambda p sigma 1, like where sigma 1 talks of one set of discrete labels, could be psi lambda p sigma 2, and so on. And right now all you can say at this stage is U lambda acting on psi p sigma must be a superposition of them with appropriately chosen coefficients, and these coefficients have been written down here in this particular form, C sigma prime sigma lambda p. If any of you are wondering about why the order of the indices is sigma prime sigma and not sigma sigma prime, I would urge you to look back at the way in which operators are replaced by matrices in linear algebra. It's exactly the same thing being done here. We will also talk about why we do this quite soon in a slightly different context, but the basic idea will stay the same. I'm sure most of you have realized this already, but just for the sake of completeness, let me mention that the reason why we are focusing so much on what happens to these wave functions under Poincare transformations, or in this case under Lorenz transformations, is that according to the special theory of relativity, these transformations are bound to be symmetries of all physical theories. And because these transformations are symmetries, they cannot change the identity of the particle. And hence, if one observer sees one particle, another observer has to see the same particle, may be described by a different bunch of wave functions, which is what helps us to identify this bunch of wave functions as describing the same particle. Now, it may so happen that two bunches of wave functions which belong to different blocks of these Poincare transformation matrices, so to speak, are connected to each other by some other symmetry. Some other symmetry combines them. Now, if that symmetry is important enough, you may have to consider those two blocks as not describing two different particles, but two different states of the same particle. We will see examples of that soon. In fact, there is a very important physical particle, which, had it not been for an additional symmetry beyond the continuous Poincare transformations, would have been described by only one wave function, or would have had only one state, but actually ends up having two because of another symmetry, that is parity. This happens to be a very familiar particle, but I don't want to give away the game right now. Our aim, of course, to understand this one and indeed all other particles, would be to find out these numbers, C sigma prime sigma, which depend of course on lambda and p. And they should of course depend on the algebra of the Poincare transformation. So ideally we should be able to start from the generators and the combination rule and be able to, ideally we should be able to start from the generators, their commutation rules, and the combination rule for Poincare transformations, and figure out these numbers. Given the fact that you have 10 parameters in a Poincare transformation, 10 generators with not really very simple commutation rules, this seems like a very difficult task. There is actually another reason why figuring out the coefficient C sigma prime sigma directly is a bit complicated. Apart from the fact that the algebra itself is pretty large and all that, the other problem has something to do with the number of parameters involved here. Well, if you look at what we were trying to do, you were starting from this relation u lambda psi p sigma. We knew that this has to be a superposition of states with momentum lambda p, so psi lambda p sigma prime, and we had c sigma prime sigma, which depended of course on lambda and p summed up over all possible sigma prime. And we wanted to figure out these numbers. However, note that we can also think of it this way. P and sigma are actually together to be seen as the index which classifies the particular wave function we are talking about. So is this pair which is a real index here? Well, actually it's way more than a pair, because sigma itself can have many indices in it. But for the time being, let's think of sigma as one entity, which for single particle states only takes discrete values. However, momentum p takes continuous values. So here we have two indices, one of which takes discrete values, the one which we actually treated as an index in this formula. The other takes continuous values, and that is the reason why we put that p essentially as an argument. However, in general, what we can think of is something like this. We have a transformation, in this case a Lorenz transformation, acting on some vector in your space, characterized with this pair of indices. The result is a vector in your space, so you should be able to write this in terms of such vectors with some coefficients. The sum will be over p prime and sigma prime, and the coefficients really will be something like this. If you think about it a bit, this is really the same as this expression written here. We already know that this vanishes unless p prime equals lambda p. So basically you don't really have a sum over p prime here. You just have a sum over sigma prime. P prime is a fixed quantity. But notice that the matrix that you now have is indexed by these paired indices, and among the paired indices you have one variable which takes a continuous set of values. P prime, of course, is determined the moment you determine P, so that's not really much of a concern right now, but you have infinitely many possible values of P. So basically we are looking at infinite dimensional matrices here. That always is a big task. The method that we are going to talk about actually tries to avoid going into that and deals almost always with finite dimensional matrices, or at least much simpler quantities than this one. It turns out that there is a way of simplifying this task by using something which is called a method of induced representations, or somewhat more informally, method of the little group. We are going to describe that particular method, not in general, but in the context of the Poincare transformation now, which will help us to see that these numbers C sigma prime sigma can be found out if we can figure out representations of smaller, simpler groups. Thankfully, what will happen is, for most cases of interest, these simpler groups are actually groups for which we already happen to know the representation. Even if you don't know any group theory, I'm pretty sure you know the basic representation for at least the most important case. If you have studied any angular momentum in quantum mechanics, you have seen that representation. But we are getting ahead of the story. Let's first talk about the method of induced representations. So that's what we are going to do next.